in the aldol. Okay, so notice we're not going to react this with that. The charge differential between these two and these two is the same. Negative plus neutral, or neutral plus positive. Okay? So the driving force, Coulomb's law, is the same in terms of reacting. And so then, in the crucial coupling step, the enol will attack the iminium ion. And the first step of that will be actually the neutral amine, which under acidic conditions, H+, this is not under acidic conditions, will give you first the salt. And only on workup then we liberate the amine. Often in a synthetic scheme, when you use this as vocabulary, you write just a neutral amine. Okay? And notice this is the bond that's made. And notice this is the nitrogen analog of the aldol. In the aldol, this would be OH or something like that, or some alcohol. Okay? And the ketone, whatever ketone you would have used. Okay? So that's the analogy that comes up here. So again, it's a twist on an existing concept that we have used off and on in various scenarios. There's an electrostatic potential map picture of the enol. Notice the enol has a lot of orange here. It's a lot of charge on this double bond. And of course, this is positively charged, so it can't help but being blue, because that's what comes out in these electrostatic potential pictures. And that gives you the final product. So we'll have a movie of that, which actually shows the individual steps that I left out once over. And so here's the amine plus aldehyde reaction, nucleophilic attack. You get the zwillerine, plus here, minus here. Proton falls off. You protonate here, or you can do it the other way around. And that is the hemiaminal, that product. Okay? So that's the addition product of the amine to the aldehyde. Then you turn this into a leaving group. Leaving group leaves, and you get the iminium ion, stabilized by resonance. And that is now the electrophilic component of in the Mannich reaction. So the hexanone turns into the enol. By the way, notice they did the Battle of Hastings on this one, which is not allowed really, but that's the way it goes. And then you get the nucleophilic attack to the carbon-nitrogen bond. And on workup, you deprotonate and you get the neutral species, or if you don't work up, that proton winds up on the nitrogen to give you the ammonium salt. Okay, so initially in your pot will be the ammonium salt, and then you neutralize to get the free base, as it's called. And the third reaction is reaction with nitrous acid. And this also has some analogy. And the way we're discussing it here, actually, it will not have any synthetic significance. It will become more significant when we do this reaction on benzene amines, okay, anilids. In other words, aromatic amines. For alkyl amines, alkane amines, this is pretty useless, or at least for general organic synthesis, there's some specialized applications. But we're covering this here because it's part of amine chemistry. There's some interesting twists. So this is a reaction where sodium nitrite is used as a source of nitrous acid. So sodium nitrite is the lower oxidation state of nitrate, one oxygen less. So instead of NO3 minus, we have NO2 minus. It's ubiquitous in nature, and it's used in chemistry as a source of nitrous acid, simply because this is a salt, stable, you can weigh it out, and so forth. So you dissolve it with the added acid, and it sets up an equilibrium, or dissolves as nitrous acid. And then in the presence of sufficiently strong acid, which doesn't have to be all that strong, you protonate to turn the OH into a leaving group. The leaving group leaves as water, and you get NO+. You get what's called the nitrosyl cation. Now, this should look sort of familiar to you. Okay? This is something that should remind you of electrophilic nitration of aromatics. There, we used nitric acid, where instead of this beast, we had an extra oxygen on that nitrogen. Okay? An extra NO bond, where the nitrogen is now N+, and the O is minus because of valency. Okay, so we have to the octet rule enforces a dipolar structure. And remember, that one we protonated on the OH, and the water was leaving, and we got NO2+ as the reactive intermediate. The electrophilic species, the nitronium ion electrophilic species that attack benzene to make nitrobenzene. So this is completely analogous to that. It's just one oxidation state lower, mechanistically identical. Now, because there is one oxygen less on this nitrogen, this is actually slightly less electrophilic than nitronium ion. But it's still electrophilic enough that it will react with a reasonable nucleophile, in this case, a much better nucleophile than benzene, namely an amine. Notice also that this is isoelectronic with carbon monoxide. Okay? This is positively charged because it's one over to the right from carbon, but otherwise it's got the same number of electrons. Carbon monoxide, of course, is neutral. And if you compare this resonance structure with this one here, you can see the analogy. But since this is charged, it's much more electrophilic. Okay? And it reacts with amines. And we'll see separately what it does with primary amines, because it causes havoc and gives you horrible mixtures. And this is why this is not particularly useful. With secondary amines, it's actually reasonably well behaved. The nitrogen lone pair attacks the NO+. Well, let's pick this one. And you get an NNO bond, and since this is neutral, the plus charge now sits on this nitrogen. This guy loses a proton, and you get this species here, which actually is a stable entity. It's called a nitrosoamine, or N-nitrosodimethyl amine is the name concocted for this. Now, they're not particularly useful, except for some special applications in synthesis, but they're of general educational, if you wish, interest, because these are species that are implicated in the carcinogenicity of cured meats. Now, how does this tie in with anything? Curing of meat was invented around 18th century or so in order to prevent botulism. So it actually preserved the meat and protected it from organisms and caused a major decrease in death from eating meat. In fact, there was a term called sausage death, because people would eat contaminated sausages, and there was botulism, the organism that would infect you, invade you, and kill you. Okay? And so sodium nitrite was found to be an additive that cause the so-called curing of meat, sodium nitrite or sodium nitrate, which with certain enzymes is then reduced to sodium nitrite. But it's this beast here. Okay? That was added to the meat, and it was an antibiotic, if you wish, and protected the meat from invading organisms for a certain length of time. One side effect of adding sodium nitrite was that the meat maintained its nice pink color. Okay? And the reason for that is that it stopped the degradation of the iron complex that gives rise to the red color of meat and the red color of blood. So our blood is red because there's actually an organometallic compound in there, which is based on iron, that binds oxygen, okay, very slightly. It's surrounded by a big ligand called a porphyrin. We'll see that in a later chapter. And then it's embedded in a huge, in fact, in sort of scale, it would be the entire lecture hall here, protein called hemoglobin. Okay? And it's sitting in there, this tiny iron, and when the blood passes through your lungs, it's pumped up with oxygen, and it picks up the oxygen and binds it. And the binding to oxygen is weak, so that it can release it whenever is required. And so basically that's the fuel reservoir, the gas station. In the lung, it pumps up the blood with oxygen. The oxygen goes around the body. Whenever it's required, it releases the oxygen. That's why compounds like hydrogen cyanide or sodium cyanide, potassium cyanide are so toxic, because cyanide also binds extremely well to iron, and it basically blocks the oxygen uptake in your blood. Now, NO and carbon monoxide, actually, is another poison that is well known. They all bind to that iron. And so NO does the same thing and forms a stable complex in the meat, which is also red. So it preserves the red color of the meat. And people found that appealing. And it's appetizing. And we are completely used to this. You think that the nice pink steak that you see at the supermarket and the color of the sausages that you buy and all that is natural. No way. If you weren't treating the stuff with sodium nitrite, the meat would actually look gray. And people wouldn't buy it because they would think it's gone off. Okay? But that actually would be the natural. If you want to be natural, this is the way to go. You would have to not add sodium nitrite and eat gray steaks. Okay? People absolutely don't like that. And this came to some controversy in the 60s when people found that nitrite addition through a reaction like this, nitrites would react with amines in the body in living organisms. So these were tests done on mice and rats, and they cause cancer. And there's a mechanism that was written for this that involves splitting off this methyl group by oxidizing it to the alcohol. And then once this is an alcohol hanging off here, then it's actually a heniaminal, and you can see that this carbon would come off. And then this thing rearranges to an alkylating agent, which there's a lot of conjecture that alkylates your DNA and causes cancer and all that. So there was a strong push to reduce the amount of sodium nitrite that is added to your food, to your meat. Okay? But then very quickly people found out that actually sodium nitrite is everywhere. And in fact, your own body produces a factor of 30 more sodium nitrite and nitrosamines than that generated by the addition of the meat color enhancer. Okay? So it became sort of a stupid argument in terms of risk assessment. It just doesn't make any sense. But there's still a very strong push by people who just don't trust anything chemical, and which, they may have a point at some stage, but also they don't trust anything that is based on reason, and that's risk assessment. Okay, so then there the argument just goes wrong. And remember that these were studies done on animals in a laboratory environment where they were, fed excessive amounts of this material, and there's the whole controversy as to what all of this means. And, rightly so, people, when they discover anything, you want to publish that and say maybe we should be careful with using this. And that makes sense. In this case, since the body itself is producing nitrosamines, and they're all over the place, and they're also in your vegetables, for example, cauliflower and spinach and so on, contain nitrosamines. It's an environmental compound. It appears, therefore, that we have evolved to deal with that as an invading, potentially nasty chemical. As indeed, we have evolved to deal with our whole environment, which is really extraordinarily nasty. Okay? So nature is not at all green. It's warfare. Okay? And we have evolved to fight and fend off or deal with the invading chemicals. And so part of what we have evolved with is that our first line of defense, and remember, this is the first intake of all of these chemicals that come in, food. Okay? And so our entire skin structure inside your mouth, your esophagus, and down all the way down to your stomach is cannon fodder for invading organisms. They just come in there and start bombarding it with all kinds of nasty reactions, and it's discarded. And there's layer 1 behind that as I speak. There is layer 2 already fully ready to take over when the first one is, or the top layer is thrown away, it's torn to shreds. And there's a third layer almost completely finished behind that. And so it's sort of like 18th century warfare where these soldiers, Napoleonic army, they would all line up and then, they would start shooting at each other point blank, and the first row would fall over, and the second row would come up, and then the second row would fall over. This is what happens in your on the surface of your mouth and first exposure to the incoming chemicals. Apart from that, there are all these repair mechanisms for DNA and so on. Okay, so we've evolved to deal with a lot of this stuff. So the question is where is it important to take a stand? That is the tricky bit, and that's where the arguments rage. And I think that's the way it should be. Anyway, so that's then nitrosamines for secondary amines. If you do this to a tertiary amine, it just stops here because there's no proton, so you can't go neutral, and it just makes the salt, and that's a stable compound. All hell breaks loose when you do this for a primary amine. When you attack a primary amine, so you have RNH2 and you attack it with NO, you lose a proton. So let me go back here. If this were a primary amine, there would be a proton left here, okay, and so you would have a metal NH-NO. This is what I have here, RNNOH. Okay? So that's the initial adduct of the nitroniumine after deprotonation. In this one, because it has a proton here, can rearrange. And what you're seeing here, this is not a mechanism you need to remember, is a mechanism that is reminiscent of the Wolff-Kishner reaction, where we had a similar scenario. This has an NN bond, and NN bond type compounds, if they have a chance to make nitrogen, somehow by trickery put in 2 additional bonds, they will do so because there's an enormous driving force for kicking out N2. And that's what we did in the Wolff-Kishner reduction. And a similar thing happens here. Under the acidic conditions, you cause tautomerism of this proton jumping from this position over here. This is, after all, again, an allylic system. So you protonate on oxygen, get this species, 2 resonance forms, and when you look at this resonance form, you realize you can deprotonate here. So protonate on oxygen, deprotonate on nitrogen, that gives you this guy, where the proton is migrated from here to here. This is called a diazohydroxide. And this guy already smells blood because now it's got an N double bond. Okay? And it knows it can make a triple bond by making this, turning this into a leaving group by protonation. And then water leaving, and you get this guy, which has an N triple bond, but the R group is still hanging on for dear life. This is a so-called diazonium cation. These guys, for alkyl, actually for any systems, are explosives. Okay? For alkyl systems, including methyl, this guy is such a good leaving group. In fact, I call it the world's best leaving group. It just takes off regardless of what it's leaving behind. And so a methyl cation, no sweat, doesn't care a damn. Okay? Just takes off. And for an alkyl species, primary alkyl cations are extremely reactive. SN1, E1, you get double bonds by E1. They react with the cations around to polymerize and the like. So that's why when this takes off as nitrogen, this guy gives you complicated mixtures. This will become important for the exception when R is an aromatic compound, benzene ring, an arene ring. Then you actually get reasonably stable diazonium ions, stable at room temperature. And they can be used as precursors to aryl cations, where the N2 leaves and you get a phenyl cation or aryl cation, which can be trapped by nucleophiles. So we'll revisit this in the next chapter. Yeah.
So how did you get to here in the first way?
So this is the nitration reaction with NO+. Okay? So NO+ attacks a primary, I should really show this separately, a primary amine. You get this guy with a proton here. Okay? One of the alkyls is proton, which is exactly this. Okay? And so that guy continues because of this proton here. All right, so this is a good place to have a break before we launch into the next chapter. Okay, so now we're returning to aromatic chemistry. In chapters 15 and 16, we focused mainly on the benzene ring. And we asked, particularly when we looked at directing effects, what do substituents do to the benzene ring and its reactivity? And we learned about activation, deactivation, ortho-para directing, meta directing, and the like. Now we're just going to turn the question around, and we're going to say, what does the benzene ring do to the reactivity of substituent atoms right next door? A position called the benzylic position. And there's a model of a substituent on a benzene ring that is turned into an sp2 hybridized carbon, which will be a key player in the next few minutes. And you can see clearly there should be delocalization. There's something special about this position, and that's why it's called the benzylic position. And as we evolve in the next few minutes, you will see that what I'm doing is I'm repeating my first lecture, except instead of allylic, I'm now saying benzylic. But everything else is the same. Okay? So bear with me. There's nothing new here, except that instead of having just a simple double bond, we now have an aromatic ring. And there are some slight differences between the fact that you have a double bond in an allylic system versus a benzene ring. But in terms of reactivity changes, they are essentially the same, or even quantitatively very, very close. Some slight differences, which we won't be concerned about. And so here we have the allylic system, and remember, it's the double bond next to p orbital. And here we have the benzylic system, which is a benzene ring next to this orbital. And they're all stabilized. Okay? And so the consequences are the same as those discussed for the allylic system. For starters,